Well, thanks very much, James. And I'm really delighted to be joined today by Sophie Choe and Steve Bissett, who are experts in this area of AI infrastructure in the future. Sophie, from the point of view of new hardware infrastructure, and Steve, from the point of view of new energy infrastructure. And I'm going to start by framing the problem statement for them to address with a few slides. And that problem is that generative AI specifically is really spiking the compute resource requirements and the energy requirements that go along with that by a factor of 4x every year. And just today, I was watching Andy Jassy talking about it on TV, and here's what he had to say.
That continues to grow. It's really the folks who have built, have an idea for a new application, but they need a lot of chips. Where if we don't have the capacity, we have to give them what we can give them and give it to them as fast as we can, and push our partners to get it in sooner. And they can't get their initiatives done as quickly as they want to if the capacity isn't there.
Anthropic.
So that's the point. People can't get their initiatives done as fast as they want to if the capacity isn't there. And he went on to talk about Anthropic and how he's working with them, and they're using more than 400,000 of Amazon's own AI accelerator chips for their next model that they're doing jointly. Just amazing. So no matter what you hear about DeepSeek and all the rest, there's just this tremendous appetite for infrastructure, and they're actually having to throttle what's being demanded by developers and users. And we see this over time. When we went from GPT-3 to GPT-4, there was literally an order of magnitude increase in every different way you can measure it, from the number of parameters to the floating point operations per second for training to energy consumption, an order of magnitude all along the board. And one of the things that's driving it is, as the costs are dropping because of all these open source innovations, not only DeepSeek, but many other similar things that are dramatically lowering the barriers to entry and the costs, this is proliferating out into smartphones and other edge devices. And so the ubiquity is going to drive ever more demand for more infrastructure and more energy. And so this is where the concept of Jevons paradox comes in. There's been a lot of talk about this since the DeepSeek shock of January 27th. I heard the head of Microsoft first talking about this. As technological improvements increase efficiency of a resource, the consumption of that resource tends to rise. And we've seen that with highway construction in Southern California. More highways creates more congestion. We see it with LED lights. They use less electricity, so now you see lighting everywhere. High-speed internet, everyone's streaming, playing games, more bandwidth than ever is being consumed. Cloud storage, everyone saves everything, more data consumption. That's Jevons paradox. It definitely applies to AI infrastructure. So I'm going to hand it over to Sophie, and she's going to address specifically how generative AI and transformer technology is driving new innovations in some particular interesting areas of hardware. Sophie?
Hi, everyone. This is Sophie Choe with qAIntum.ai. So you saw from Dan's graph this hockey stick jump in the era of deep learning. So once we had neural networks and the capacity to layer however many layers you want to layer, now actually we have a deep machine learning model. Now it's embedded in transformers that are propelling this Gen AI revolution. So before this transformer architecture that came out of Google Lab in 2019, all the machine learning algorithms, they could do classification or regression, single output. But with transformer, now you can actually have a long sequential data that can be used for content generation in terms of text or images and what have you. So when you actually go inside the architecture, now you have multi-headed attention. But even with the input, instead of just using input, now for each entry of the input, now you're putting positional embedding, encoding to know the context of things, each entry's relation to other entries. So the input information input vector got much longer. And then you have multi-headed attention where you're dot producting. So each component is going to be compared in relation to other entries of the data. So that's very, very compute intensive. And then you have feed forward block, which is neural networks. Again, a lot of parameters train. So with transformers, now we are able to extract contextual information at a very, very high computational cost. Next. For example, the structure of large language models, this was developed by OpenAI because before OpenAI, Google was playing with BART, which was stacks of transformers, blocks of transformers. You see in the diagram. Only that portion was what BART was doing at Google. But then OpenAI came along. They put yet another neural network as supervised learning. And then thereafter, reinforcement learning, which is gaming and scoring the output with the human feedback to get most desirable output. So in all these layers, inside transformer, we have multi-headed attention, matrix multiplication, and then we have neural networks, supervised learning, massive neural network, and then reinforcement learning with implemented using neural networks. Just the number of parameters for training is growing substantially. And then when you have a model for inferencing, you're not training the parameters, but you're using those parameters to compute to get the answers you want. That's kind of like behind what's driving this chip demand surge. Next. So now, GPU with the NVIDIA, they had a really strong ride and what have you. So, but we can't rely on just one single vendor. There's a lot of research going on by a lot of researchers, and silicon photonics is one of them, using photons as information carriers. The advantage of using photons is that you have high bandwidth input and output. And then anything can be very easily multiplexed and networked using optical fibers. And within single fiber, you can do wavelength division multiplexing to kind of divide for multiple packets information passing through, and it has low latency, and then photons consume less energy. Next. And then we can even go explore the quantum world with photonics. There's a company called Xanadu up in Canada. They developed a very small size, room temperature, quantum photonic computer in around 2020. So when you're using quantum computing in the quantum mechanical world, things are not definite. Things kind of exist in quasi-probabilistic state that we call superposition. So what that gives us is massive parallelism because we have to consider all existing states simultaneously. So there's a lot of effort happening to go beyond CPU, GPU, TPU, and what are the other modes of chip production that we can come up with to meet the demand propelled by this AI, Gen AI especially, revolution. I'm done.
So thank you very much, Sophie. So with all these advances happening with photonics and with quantum, there's still an insatiable demand for energy. And Steve, I'd like you to now speak to that, and I'll hand it over to you.
Okay, thanks. First, thanks for having me here, and I'd like to say it's good to be talking, back in the Intel or ex-Intel world again. I probably left before most of you joined Intel, but I spent many years providing equipment to Intel, test equipment, and in the sense of providing electricity to data centers, I think the wheel is going to come full circle there. So, just without belaboring the point too much, just to summarize what the issue is, might seem a bit overly simplistic, but data centers are being built. There will be far more data centers built in the next 5 years than exist today. The typical power consumption, like the median point, seems to be around 200 megawatts, which is about 200,000 or 300,000 houses worth of electricity. It's massive. And from an electrical power supply point of view, a data center is just a resistor. So you're pouring all this electricity in to gigabits to do computing, and it gets hot, and you have to then take the heat out, or else the chips get too hot. And typically, roughly speaking, 50 or 60% of the power that goes into a data center is to make the computing happen, and then 40 or 50% is to get the heat that generates out again. But you've got a massive electrical load or a mixed electrical and cooling load. You usually use electricity to create the cooling. So the issue is that the demand for this is just, going up, and it's already reaching the point where people building data centers are finding that electricity is their limiting factor. It's either chips or electricity. The chip supply goes up, and in some senses now it's easier to expand production capacity of chips than it is to expand the electric power availability to run the chips in data centers. And it's a mix of, there's not enough power generation on the grid, and the transmission wires don't have enough capacity to get that transmission, to a data center. There aren't, people just haven't built an excess 200 megawatts here and there that's just lying there unused. It just doesn't happen. So the growth of data centers is going to require a lot of construction of new power generation plants and construction of grid capacity if the power is connected to the data center through the grid. So anyway, who says this is a problem? I'm not going to read any of these things out, and this is a random selection. You can find dozens more of this in all kinds of press anywhere, but basically this data in general and AI in particular generated limiting problem of electricity is, we're bumping up against the limit now, and that creates problems, and it creates, certainly from my perspective, opportunity. So next. So yeah, how much? The forecasts are all over the place, and I gave Dan this slide last week, and I found a whole bunch more, but it's pretty chaotic. But they're all big. No matter who's doing the forecasting, it way exceeds the capacity, and it exceeds the expected capacity of available electricity at the right sites over the years. And so, just to put that in perspective, that dotted line is California expecting its, steady year-over-year growth through 2030. That's the entire state, all consumers of electricity. And the other lines are forecasts of added electrical demand added per year, whereas that dotted line is the cumulative total. So you can see we're smacking up against the problem. So next. And there are two limits. One is how much electricity is available. And by the way, there are two issues. As I said, there's the input of the electricity has to be electricity to run the chips, and then the cooling, which is typically say 40%, can be done electrically, the way your refrigerator runs on electricity, or it can be done by heat. with what's called an absorption chiller, where you're basically using heat to create cooling, and uses refrigeration principles. But when there's heat accompanying electricity generation, that can be a real opportunity if the power plant is right next to the to the data center. So, one of the things that is even slower than building new electric power generation capacity is getting transmission lines approved and put in place. You hear all sorts of numbers depending on the case, but from when you say go to having new transmission capacity can easily be 5 years or more, as it can for certain types of power. So one solution to that is co-location. I think this people waking up that this is going to be, more and more the dominant mode of data center growth, and it'll affect where they're put. But if you put the solar panels or the geothermal or the nuclear plant or whatever it is at the same site as the data center, then you don't have to build a new transmission line to connect them. Connecting the wires across a few meters or a few hundred meters is not an issue. You don't have to deal with the grid. You're still going to be connected to the grid in most cases, but you're not looking for massive capacity increase from the grid. So this co-located mode, I think, is going to be really dominant, and it's definitely never going to be a one size fits all in terms of the power. So if you're thinking, which is going to be the winner, there will be, from reviving old nuclear plants that'll solve a couple of problems, but not on a big scale. New hydroelectricity takes forever to do. One of the dominant co-located technologies is solar panels combined with batteries, because you don't want to just run the data center during the day. It's very expensive, but it's available. It's one of the most scalable, ways to build new capacity. Another really interesting technology is what's called enhanced geothermal. You might have heard about a couple of companies, Fervo and XGS, where it turns out if you dig a hole in the ground far enough down, it gets hot, and so you can use that to source heat that you can use to generate both electricity and cooling. And then there's small modular nuclear, which some people are really excited about, but it's going to be, depending on who you believe, it's going to be 5-8 years before there's really capacity at the scale that data centers need. And there's even, talk of nuclear fusion. So I'll just finish with the punchline of what the qAIntel guy is doing in this space, which is next slide. So we, Turgil Energy, the company that I co-founded, are developing, we're about 90% of the way through the development cycle of a modular power station, for 5 megawatts. So for a 40 megawatt data center, you need 40, for 200 megawatt data center, you need 40 modules. So it's scalable in that sense. And so we harvest sunlight during the day. We store the energy as heat. We use the heat to generate electricity and also to provide cooling. And if you're going directly from heat to cooling, that's cheaper than going from heat to electricity to cooling. And we have worked for years at this, at making it not deep science, but simpler and simpler. And the thing about simple technology, and where we rummage around in the drawers for old technology and figure out a way to configure it and architect it to make it cheaper than the new technology. And the convenient thing about old technologies is that they tend to have very large supply chains that have been developed for them. So this affects the scalability issue. And just in terms of costs, the graph is the assertion on the right, where the three bars on the right are the cost of solar panels that charge batteries, sort of the low, medium, high, according to the National Renewable Energy Labs. And on the left is our apples to apples comparison. So we think we can scale faster for half the cost. But that's I'm done.
Great. Well, thanks very much, Steve. Now, before we go to the question and answer stage, I want to give our audience an opportunity to see how they can get in touch with you guys, Sophie and Steve. You can see the LinkedIn profiles, the websites, and the email addresses at your companies. And I'll just keep this on the screen for a few seconds here. And as I do that, I'm going to throw a question to both of you. And then after we have a few minutes of conversation about that, I'm going to hand it over to James, who's been curating questions coming in from the audience as you guys have been speaking. And we'll hand it off to James to ask you those questions. But let me stop sharing the screen and throw you my question first. And that is, Wall Street has a lot of real smart people. In fact, a good friend of mine is a hedge fund guy, and he's one of the smartest people I know. And, ever since January 27th, with this big scare about DeepSeek, uh, despite some elements of it that have been partially discredited and other parts of it that have been validated, investors seem to be really spooked. Nvidia's gone down a lot, Microsoft's gone down. The infrastructure folks, the hyperscaler folks have really suffered because of this. So there's a lot of skepticism on Wall Street right now among a lot of really smart people who analyze all these things. You guys, Sophie, Steve, are both betting your companies, your CEOs, founders of companies that are all about innovating in this AI infrastructure and energy space. So you're obviously not skeptical the way Wall Street is. So, Sophie, beginning with you, what makes you so confident that you're right and they're wrong?
Yeah, one time I was walking down the street, I was looking at the cars, and I was thinking about Henry Ford. Like, can I imagine a world without cars where you have to walk everywhere? And it was just flabbergasting. I was so grateful to Henry Ford. And I think in a way we are going through that Henry Ford moment because Henry Ford did not invent the combustion engine. He popularized by reducing the cost drastically down. So in a way, that's what DeepSeek did. But in terms of innovation, I mean, they just kind of optimize little here, little there, where they can optimize in a very clever way. But again, as I said, it was neural networks. And then the architecture of transformers was just revolutionary. And then OpenAI to add that supervised learning layer and reinforcement learning layer. DeepSeek did not change the architecture, but they just squeezed out the efficiency. And more people are going to do that even more, like vastly encouraged by what DeepSeek did. The cost is going to come down more and more. It's the same thing when you fly. Before, when you go to the airport, it was the very, very select few at the top who could afford that. Now it's like you just go there in your flip-flops and, you know, so it's, yeah, AI becomes your everyday thing. And when you're really bored, oh, let me see if I can build a foundational model for my family. I don't know. So the demand is gonna go like, yeah, it's never gonna stop.
And Steve, what gives you the confidence to think that the need for this kind of energy solution is as insatiable as you believe?
Yeah, I mean, you could give so many examples. I'll go back to the Intel one, way back. Uh, when I joined Intel, the 8080, not the 8086, or the 8080 was just coming out and was taking off, and I was involved in chipset architecture for that. And there were consulting firms who were doing market forecasts. And so what they would do is they say, okay, what's this good for? We've got Hazeltine data terminals that have a board full of transistor logic. And we can do all that with one CPU chip plus a little bit of glue. And so, this could satisfy that. So they add up those things and they draw a line. And you look at that, you go, no, no, no. This is, people are going to invent things to do with this that they would never think of with a board full of transistor logic. And this is exactly what happened. And so, the demand just shot up, and Moore's law just compounded. The same, Intel used to be primarily a memory company, and profits would be good. People all over the world would go, great, let's build some more fabs. Then there would be oversupply. Then the costs would collapse, and the stocks would go down, and would look doom and gloom. But because the memory costs were below, people would write more and more software with more and more layers, and then it would just oscillate, but always oscillate up. It would slam up again. And so, AI is, in very broad brush terms, is just the latest killer app that does more things than were done before, that were imaginable before, and it just happens to suck up an enormous amount of computing power. So, there may be sort of delays, sort of growth curves, draw the story, time going this way, tend to happen slightly more slowly than people project, and then kick up more quickly once people figure out how to apply AI, for example. And from our perspective, we're trying to get to market to be scaling up in 2027. So that's actually good. If the horse had left the barn already, that would make it harder for us. But the other thing I'll just say from the electricity perspective is, depending on which salivating consulting firms forecast you look at, whether by 2030, whether data centers are going to go from 2% to 4% of the United States electricity consumption, or go from 2% to 11%. Even at the 4%, we have this massive problem, but it's still only 4%. So we're always developing electricity to displace, fossil gas combustion, and the market for that is actually much bigger even than the wildest data center forecasts, and the need to make something that's clean and cheaper than the incumbent is still compelling, but it's not compelling in the same way data centers are, because when you showed that clip of the Amazon CEO in the first place, I mean, he has a pain problem. You've got utilities and suppliers, and they have environmental goals, and they want to save money, but do they have to get that done before they go home to work today? Whereas what this over demand that's being caused by AI does is it causes added electricity capacity to be a pain point. And we're a new entrant, and with a way of doing it that's not established, and it makes people look, well, I can't get what I need from the old way. Maybe I'll give this one a shot where I wouldn't have before. So, I think it's all good.
Well, now before I hand it over to James to take questions from the audience, I want to add my view on this. You talked about the 80-80, and I also started my career maybe just a few years after you, but not that many, when the 80-80 was the main Intel chip out there, and the Zilog Z80 was competing with it, and the 8085 was out, and all these 8-bit microcomputers, as we called them, were running the CP/M operating system that more than 600 OEMs used, because thousands of application software programs ran on it, from word processing to spreadsheets to databases to all kinds of stuff. And that's what made the hardware valuable. It was the applications that drove the market. And the hockey stick that I saw with the personal computer revolution in 1983 was 2 years after the IBM PC came out with the uh, first 16-bit, and it wasn't until Lotus 1-2-3 came out 2 years later that there was a reason to buy the darn thing. And then all of a sudden things took off. And we saw similar things happen with the internet. When the World Wide Web came out, all of a sudden everybody started using the internet, even though scientists and engineers had been using it for many years before that. Applications drive the market. And so anything that lowers the barriers to development and use of applications, solutions that deliver business value, that's what makes the hockey stick happen. And I think that's what we're seeing, not just with DeepSeek, but Sophie, as you were saying, all these related innovations that have to do with optimization and squeezing out efficiency and reducing cost. It lowers the barriers to developers like the Fusion Syndicate and to users like our customers, and allows broader adoption. And I think that's the answer to these skeptics on Wall Street. They're too short-term oriented. But I'm going to stop talking, and James, I'm going to hand it over to you.
Well, Dan, I have to say, great conversation, panelists, marvelous job, Dan, great job moderating. I have to say that I've been doing this now going over 3 years, these online events around technology, thought leadership, Intel historical perspectives, and life after Intel. And this is the first time that I have never had an Intel audience ask a question. So
We had them
either
mesmerized.
they are
Maybe it's just too
mesmerized,
boring.
stunned, it's boring, but I haven't seen a drop off much in people participating. But look, I will ask a question because at least from my perspective, when how I originally conceived of this event, and I was talking to Dan about it, I was thinking about this in terms of, the end of Moore's law, that you had that on one end, at least in my mind. And on the other end, you had room temperature quantum computing, which I've talked to you about, Sophie, pretty extensively. And then you have photonics is kind of in the middle. And I did a bunch of research on it. And it kind of sort of sounds like it's a bridge technology. And I think that since we're all kind of chip heads, Intel chip heads, how do we get from Sophie from Moore's law to the utilization of photonics, um, then to quantum, room temperature quantum, and then what is the impact, Steve, on energy demand? This is a big deal, and I think about energy demand on two scales, right? You got what you could co-locate, and it's what we all suck from the grid in our household, and does the grid need to be modernized? And of course it does. But Sophie, let's start with fundamental computing architecture. How do we get from Moore's law to where we can handle big AI workloads, both generative and ultimately AGI?
Yeah, I'm not, even though I am from ECE, I just danced around all the computer architecture classes. So I don't claim to know much. However, I was just in Texas, UTD, and I was so surprised. There's so many optics people there. And unbeknownst to us, there are all these optics engineers constantly advancing fiber optical technology and laser technology. And I was told about hollow core fiber optics. So instead of using silica for data packets, they're actually using air as medium for photons to flow through. And now you can actually put, so, way less latency. But inside, you can actually put different types of gas. And you can control operations that way, but still very early stage of R&D. But you're kind of peeking through the air into the future where things are going to be lighter and less clunky, physical stuff. So with photons, it being the most abundant resource that we can see around, and then more than anything, when you actually compute things, it doesn't create heat. I mean, Steve, it was really enlightening to hear a lot of power consumption is actually in cooling. I'm like, wow, yeah, of course.
Yeah.
Well, it's kind of one to one.
Oh, yeah, that's
Yes.
a huge problem that IT people deal with, and data center design people have figured out all these fancy ways of creating airflow and things to manage it. It's a huge issue. Yeah.
Yeah. So when you actually go back to the very basic infrastructure, starting from fiber optical cables, and we think it's done, but even today, those engineers are bringing all these innovations all the time. And then if we can have computational devices using light as information carriers, always more compatible than, like all these disparities and what have you, then it would be really, really great. And then as Steve was talking about this co-location, I started thinking, because somebody was telling me about his vision of modular, decentralized power generation. So Steve, I'm just waiting for the day where we are all going to have solar panels, but we can still use power at night because we can save in your steel vessel. So I'm just thinking about not breaking down the existing infrastructure, but slowly but surely migrating to more decentralized power system where each individual have more power. Coming back, I'm sorry, James, I kind of went off tangent, but I think we have to start thinking about different ways of encoding data processing from this vastly successful silicon that we've used so far. And there are people researching that. The only problem is that the R&D cycle until revenue generation is very, very long, actually.
Okay.
So I have a follow-up question to a point to Steve about a point that Sophie, you just brought up about the decentralized nature of all this. It strikes me it's kind of analogous to what we saw with computing, where with personal computers, that decentralized computing from the mainframe that had all the dumb terminals, you know. But then with the World Wide Web, we started connecting all these PCs, and then with cloud computing, we recreated time sharing, basically. I mean, it's kind of like we're all connected to the mainframe again in a way. And so it's sort of like, you know, first there was a mountain, then there was no mountain, then there was, you know. And I'm wondering if we're going to see the same thing happen with decentralized energy, where people are going to build these things out modularly for all these data centers, but then connect them to the grid so they can kind of have an ebb and flow of energy, and then have intelligence that connects them together so they can manage intelligently and optimize what ebbs and what flows and where and when. But Steve, what are your
Yeah,
thoughts about
I
that?
mean, absolutely. And if you're, if anybody who's in the energy or electricity world at all, this is a constant discussion. There are people who talk about getting off the grid with electricity as if that's a virtuous goal. Now, these are not people who are talking about cutting themselves off from the internet for communication. So I don't know why that would be a goal, but decentralization has a lot of benefits to it if it's done properly and up to a point, because you've got a much more resilient power structure. You have fewer major points of failure, and there's definite optimization. Now, I think electricity is one of those things where the prevalence of solar panels and batteries in people's homes has been a function of utilities being too slow to get going, and then policies and subsidizing it, doing it on your home. It doesn't make a lot of economic sense. It costs about twice as much to do it yourself, just because of all the plumbing and wiring and the guy who has to come and the cost of selling and so forth. But a certain amount of that and lots of regional distribution. But the more distributed you make it, opposed to having a few big power stations burning coal and nuclear and all the electricity going one way, is it gets much more complicated. And there's absolutely a role for AI in this, because how you mix and match electricity flows one way, there's a surplus here, then there's a shortage there, and then it switches around depending whether it's solar, wind, if the wind's blowing here, the sun's shining there, all these sorts of things. And it's very complicated. And AI is going to help. But when people think about the magic of AI, they got to realize that AI in this situation is an optimizer. It's not a generator. AI consumes electricity. It doesn't create it. And in fact, AI creates escalating demand for electricity. But just being able to manage it all so that it doesn't all fall apart is definitely where AI is going to be, a godsend. It's going to help really make it all work without getting so complicated that there are unanticipated instabilities in the system that cause it to crash all the time.
Hey, that's a good answer. By the way, Dan, we did get some questions, and
Good.
the kind of like one observation I have, because both Steve and Sophie have talked about this, is the notion of moving from hierarchy to distributed, right? Whether it's compute or it's energy generation and co-location, right? If you think about our history in technology, it's tended to go from hierarchical architectures to distributed, right? And yeah, yes, you can have hierarchies within a distributed network, but nevertheless, it's still distributed. Anyway, so Angela asks, and she's from IT and former Intel IT, how do IT leaders ensure AI workloads are efficiently distributed across the cloud, on-prem, and edge infrastructure? And by the way, Steve, I've heard that AI workloads kind of move with the sun. So I don't know if that's kind of part of the experience, because that's where cheap energy happens to be. So
Oh,
how would we answer that question to efficiently distribute it across the cloud, on-prem, and in edge infrastructure?
I would say, yeah, I would say what is kind of unsettling to all of us is that things are moving very organically, but so fast that not one single person knows everything. And that's very, very unsettling to all of us. It's like if you have a textbook, you can master maybe two or three. Now you are done. You know everything, but that's good. So that's not the case. And especially with OpenAI, it just came out of nowhere, like, whoa. And then the world has changed. And then you're like, oh, who can dethrone OpenAI? Boom, DeepSeek, and like, so I think a lot of those moments are going to come. So in the absence of information of what's going to happen even tomorrow, I don't think we can master plan how it's going to be distributed. It's going to be way more organic. So that's a very unsettling place for us to be, for all of us.
Yeah, I think AI is going to become like a utility, the same way that, the internet and the World Wide Web became kind of a utility, but in a much bigger way because it's intelligence, not just connection. And so I think that we'll be surrounded by intelligence that, it'll be built into everything because it'll be a commodity. It'll be so cheap. And the value will be how to leverage it, how to make use of it, coming up with the solutions, the applications that deliver value to people, whether it's, a consumer experience or a business solution or healthcare, science, research, education, whatever. And we're just going to see a blossoming, just like we have in other waves of technology innovation. But because there's intelligence on the other end of it, it's a whole additional dimension of blossoming. So the exponential progression is deeper, it's greater because of that. And that's why it's going so fast. But we're just at the beginning of that application solution piece of it. All the growth so far has really been about infrastructure. People are so excited about NVIDIA, and even though they've had the setbacks recently, that's I think very temporary. But that's the level people are talking about is the build out and the infrastructure. Okay, but what about the solutions? That's what the skepticism is. Where's the ROI? Where's the payback? Where's the productivity? Well, when have we heard that before, right? I mean, this is what, the third or fourth time I've heard that in my career. So I'm highly confident that we're going to see it and we're going to see it real soon.
Hey, Steve, any thoughts? Oh, I'm sorry, Sophie. Go ahead.
Yeah, I just wanted to add, just like software development, waterfall versus agile, I think we just have to optimize things today. We can't really master plan because it's not the space of AI and compute resources. It's not static. It moves. So we have to move organically together with it, I think. That's my answer to Angela.
Yeah,
Steve, any
and
thoughts?
yeah, look, I'll try to not ramble on here. I took that as a question about optimization, and people will have spent a lot of money on computing resources and the power to operate them in different locations, and in this very chaotic and unpredictable way, the computing loads is going to be, variable and generated from different sources. And, there are plenty of startups who are saying, we have AI that can figure out how to, they're going to try to sell these products and get venture funding and sell the products to data center operators, to help manage this stuff. And but it's an optimization problem. And I'll just mention that, that in any engineering problem, what's optimum what's the most optimum is not necessarily the most efficient. And sometimes the architecture that's a little bit simpler and where the resource isn't fully utilized 100% of the time, um, may end up being better because you can scale it faster and get down the cost curve faster. So you've got cheaper stuff being used at 80 or 90% capacity instead of focusing on how do we get 100% capacity utilization of something that's going to end up costing more, even though it's more efficiently utilized. But all this stuff is going to go on. I mean, there are tons of innovation, tons of startups, and it's that question is going to be continually answered over the coming years. It's never going to be answered perfectly, and the answer is never going to be static. So,
Well, hey, Dan, we actually have a couple more questions here from Bob. Bob, I apologize to you up front if I butcher the question, but I think it's a two-part question. It's one is really about energy transition from more fossil fuel oriented towards more renewables and nuclear, and what is really realistic, right? In terms of time frame, is it a year from now? Is it 10 years from now? Is it 5 years from now? And the other piece of this is, when we talk about distributed bidirectional energy generation and distribution, is the internet the internet TCP/IP, is it a way to distribute it, to create a highly distributed energy model? First question's about energy, carbon to something else transition. The other part is, what does the future architecture look like for energy distribution?
Can I
And I
say
think
I've
well,
seen TCP/IP over power wires, but that's the
right.
opposite of what you're saying. Go ahead,
Yeah.
Steve.
So Steve, you're the pro on this.
yeah, this is an area where I warn you, I have uh, a lot of knowledge and even stronger opinions.
Uh-oh.
Um,
It's
uh,
okay. It's okay. We're all friends here. We all know
but
each other.
it's a really good question because especially if you get your information from reading the press, who have to make things exciting,
Yeah, yeah,
and
yeah.
and so this question about, you know, I mean, to paraphrase it, you're saying what's realistic in terms of transitioning from fossil fuel to renewables, and back to the subject of this session, what's the role of data center construction in doing that? And there's sort of a lot of well, this is going to happen. Well, that is going to happen every day. Somebody makes a headline in the press. So, but what's clear is that it is going to cause a bunch of capacity construction, both in transmission and in generation. I've asserted that there's going to be a lot of co-location in terms of generation simply because it'll just take too long to do the transmission construction, but there'll be a lot of that too. It's not either or. And then in terms of, what can you co-locate or what can you put on the grid when there is new transmission capacity? There's a lot of excitement about, Google putting money into geothermal or small modular nuclear reactors and so forth. And, different excited forecasts about when that'll be available. I mean, I think the most realistic is that, for one thing, from what I can tell, uh, even though, I mean, this gets into the matter of opinion. I think it's unlikely that nuclear will suddenly become as cheap after all these decades as people are forecasting. I think going this small, this is what we're doing, is taking very large power stations and making them small and Model T Fordish, and that's their plan, and that's a good plan, and it'll get somewhere. But will it get cheaper than solar with storage or wind with storage? And that's a race because both of those things are coming down a curve. And I kind of predict there's not really that much of a future in the next 10 years for future because they're constantly going to be struggling with the availability of viable, lower cost alternatives that are clean and cheaper than fossil fuel and cheaper than nuclear, that arrive sooner, and that the data center and the electricity market in general can get their hands on. I think enhanced geothermal it has a real good prospect of starting to scale up fairly quickly, starting in 4 or 5 years. Nuclear will be a little bit longer than that. The thing that's scalable now is putting a big area of solar panels charging a big chunk of lithium-ion batteries. Now, we have a technology that does that, but we do it much simpler in a different way. We use mirrors and hot water and steam. And like I said, we rummaged around in the old dead technology toolbox and figured out how to kind of leapfrog that and make it cheaper. But it's solar combined with storage, which has its pluses and minuses. Like it doesn't work on cloudy days. We can take electricity, we can take sunlight from the day and make electricity all night, as long as it was a sunny day. But if there are 2 cloudy days, those days of the year you need backup. People say, well, that's a problem, but people solve that problem all the time. They put a diesel genset on site or something like that. So kind of the contest here, the really interesting thing in terms of this question of the transition, getting back to the core question that you asked, is that now that it's becoming clear that the capacity is not going to be there. And by the way, even with our opportunity is that with solar panels and batteries, it takes too long to build the gigafactories, to build the batteries. And besides, the supply chain's getting disrupted by tariffs and it's multinational. And the electric vehicles are competing for all the raw materials for the batteries. And so, it's not that solid of a solution. So we can kind of, our opportunity is to run past that. But that is the biggest solution right now, is solar panels, batteries. It's a multi-billion-dollar business. It's already scaling up fast. And that's what's filling the immediate co-located demand. And the competition for that is people are saying, in most of these cases, there's a gas pipeline, and we can put a gas turbine there and build our own 365-day-a-year reliable power supply with a gas turbine on site. And sorry about our corporate renewable goals, but we got to have power. Now, it turns out that the lead time for gas turbines is like 5 years. And the cost of doing it with solar, certainly our way, is actually cheaper than the gas without subsidies. So there's going to be this interesting race. But the thing that I think I'm really optimistic about is because the need for electricity and cooling is not just a desired thing as it is for the utilities. It's a pain point for the companies who have massive amounts of money and massive amounts of money to be made from expanding their compute capacity. Because this availability is a pain point, it creates this vacuum that will bring new renewable technologies such as ours, such as enhanced geothermal, to scale and drive the cost down substantially more quickly than it otherwise would, even while they're building some new gas turbines. And then that'll spill out into the worldwide market in general. That will, 5 years from now, the whole AI thing will have lowered the cost of renewables to the point where they become much more desirable in the wider market. So I think the net effect of it on the electricity transition is going to be very positive.
So
Well,
Steve, Chris has asked a few questions I saw about batteries and some of the disadvantages. Lithium-ion batteries can explode and burn, and lots of other different issues around batteries. So you were saying you have a way of kind of undercutting that. So what
Yeah,
were
and
you
for
talking about?
starters, the issues with batteries, in my view, I don't think exploding batteries, it makes a good news story, and there were a couple old tech things that were, part of the learning curve. But there used to be exploding cars too, and engineers have figured that out. What went wrong, and then they don't do it anymore. People also talk about the problem of disposing toxic materials. Well, that's just a big business opportunity, is to recycle a battery. So much as I'd like to, diss the competition of batteries, those popular issues, I think, are really not issues. What are issues? What do they cost? How much does it cost to build factories, to scale them up? And can you get the raw materials to meet the demand that the market has? And that's where the real weaknesses are. And we just to put a quick, I'll try to do this in a minute, an explanation of what we do. Most people have seen the concentrating solar power, picture of the 400-foot tower in the desert with the bright shining light and all the mirrors around it. They think that's concentrating solar power. And oh, that one's being shut down now, by the way, ahead of schedule because it's not economical. So we actually use that's the old shoebox that we've rummaged around in, where we use mirrors to concentrate sunlight on pipes. We pump water into the pipe at a low temperature. It comes out at a high temperature and a high pressure, and we store it as water in steel pressure vessels that are insulated. And then, what comes out of the pressure vessel day and night is hot water, the same as hot water comes out of the ground in a geothermal system. And we use the same, steam generation cycle to convert that to electricity. And it's all about how simple is it? How scalable is it? What are the parts cost? And if you think about it end to end, including everything from how do you put it on a truck? What's the cost of doing it? How do you stage the materials at the construction site? Can you get 95% of the installation labor out of it? The answer is yes. And those are sorts of issues. But physically speaking, our battery is a cluster of tanks that are 40 feet high and 8 feet in diameter that are full of water. And they'll snuggle up against each other, and we put a blanket around them. And it's a quarter of the cost of doing batteries. They don't wear out. We don't have any material supply problems. And it's, but it's not deep tech, it's architecture, and it's designed for the supply chain. And we've just been cranking on it to figure out over the years, which pieces of the puzzle we can put together to make it cheaper and simpler at every step. And we're not the only ones. I mean, there are other people who see the opportunity in innovating in this. So you'll see more innovation in the solar thermal area. There's actually a company called Exowatt that from a distance looks a lot like our strategy, and they just got $20 million, including from Sam Altman. I think they are a long way. I'll just go and say this. They are a long way from knowing what they're doing, but they kind of have an idea that strategically is similar to ours. And there are other people trying to do that same sort of thing. So solar panels and batteries are a solution. They're at scale now. There's huge capacity, but there are issues and vulnerabilities, and there's plenty of space for innovation to take place. And what excess demand does is it provides a space for innovation to get in and get to scale that might not be there if everything was just trundling along at a nice lazy pace, and people it's just easier for them to do what they did before. If you're ever trying to
Yeah.
the VCs with a startup, the question is, are you selling what is it? Are you selling aspirin, or you're selling Tylenol or something else? In other words, are you selling something that the customer desperately needs, or are you trying to convince them that they would like to have it? And so, new power technology has been kind of try to convince them that they'd like to have it. Green is good, global warming is a problem, let's do that. And it kind of lumbers along. So I think this excess, you know, thirst for
Yeah.
electricity, that data center is just going to be a real slingshot to
Well, it's
solve
like
problems.
what Sophie, you were saying, when there's more demand than there is supply, like for compute resource, then DeepSeek was driven to innovate the way
Yeah,
they did in software to optimize and came out with this amazing new thing that all these fat, dumb, and happy people in the US that had all the compute resource in the world, they were just brute forcing it. They didn't have to innovate like that.
yeah. I mean,
Now
somebody
they're
said
looking at a
a
new way.
crisis is a terrible thing to waste.
Well, it always is.
Exactly.
Hey guys, we're past the top of the hour, and I think we've had a great conversation here. I really appreciate everything. Dan, do you have any parting thoughts?
No, well, I just want to thank Sophie and Steve for joining us today. It's a fascinating conversation. I hope we can do it again sometime soon.
Yeah,
Yeah,
I mean,
I learned so much. Thank
Thank you,
you.
yeah, I
Dan,
mean, this is,
James,
and by the way, Steve,
Sophie.
before you go, I mean, the one thing, this one notion I want all our alumni to walk away with, it's the idea of highly distributed networks, whether it's people, energy, or computing,
Yeah.
right? I mean, I think that's ends up with being, it happens anyway. And so, with that, let me say thank you to everyone for participating tonight. I really, really appreciate it. We have another event coming up March 12th, which will be focused on the 2-hour job search put on by Gina Riley Consulting. Again, she is a fellow alum. This will be the 5th in our series for career transition. As all of us unfortunately know, Intel has been going through a very difficult time. And we have seen both a spike in membership and a huge demand for getting help figuring out what the next thing folks are going to do with their lives. And with that, Dan, I think we can call that a wrap.
All right. Thank you, James.
So panelists, please hang on. Everyone else who's online, thank you so much. You guys can say goodbye to us. We will talk to you all later. And with that, this is the end of the formal part of this discussion.